Homogeneous differential equations. We're actually going to learn about 3 types of differential equations in this unit. It's a mini unit, so after this we'll be 2/3 of the way done. These are very specific types. Right? They follow a very specific structure. Here it goes through how you can actually determine whether a differential equation is homogeneous, but that's kind of a different story for a different day. Today we're going to deal with cases that we know are homogeneous and actually differentiate them. All right. The idea is that we're going to take differential equations that are not proportional and force them to be proportional by introducing a new function that will act as a proportionality constant. You know, it'll behave as a proportionality constant would. Right? So that's what we're going to get into in a few minutes. But you look at this and say, okay, I know how to solve a differential equation by the separation of variables. All right? So the issue would be I can't separate the x squared and the y squared because they're connected not through multiplication or division, they're connected through subtraction. Subtraction or division or addition makes it so that you're unable to separate those variables. But by introducing a new proportion, y equals vx, where the v function acts as a new function that is proportional, that creates proportional relationship between x and y, we're going to be able to modify the original differential equation into a new form that will be separable. Right? The idea behind it is maybe you can't transform one function into another by just multiplying by a constant. Sometimes you can. You know, if I had something like x and 2x, right? X and 2x, they're only differing by a constant multiple of 2, right? So this is a proportional relationship between x and 2x. They're in ratio of one another, right? But then you get into y equals 2x, where y has a proportional relationship with 2x. But then sometimes you get into something along the lines of, let's say, x and sine of x. Is there any way I can correct an x function to make it into a sine function? Well, not just by multiplying by a constant, right? I can't just multiply x by 2 or 10 or negative pi or something like that to make it into a sine function. I have to multiply it by an entire other function and even divide it by another function in order to make it into a new function. That's the role that v is going to play. It's a new function that modifies the existing relationship in order to make it proportional. The issue that we get from this is the idea that, okay, we don't just have y's and x's, we have dy's and dx's, right? So we'll have to account for that. So I'll do that by taking the derivative of this with respect to x, all right? So left-hand side is dy dx. The right-hand side I have to differentiate implicitly. All right, so I'm going to apply the product rule. The first function, which is v, multiplied by the derivative of the second. Well, what's the derivative of x with respect to x? 1, so I'm going to leave that alone. Plus the second function, which is x, multiplied by the derivative of the first. What's the derivative of the v function with respect to x? V prime, or we could say dv dx. dv dt, wrong class. That's 7th period. They're doing related rates now. Remember putting that in a rear view window as quickly as, rear view mirror as quickly as possible. Yeah, they love it. Anyway, so what I can do is I can swap out a lot of ingredients from this equation, but I do want to clean it up first because it's in a pretty hideous form. So I'm going to rewrite my original function. I have this model to work off of. This is a standard rule now. We're going to use this in any case that's homogeneous. All right, but I'm going to go back to my original function, x squared minus y squared, my original differential equation. 3xy dy equals 0. I'm going to solve it for dy dx. The reason why I'm going to do that is because it's going to make it much easier to perform a substitution. Right? Because if I need to substitute into my rule, my differential equation related to y equals dx, well, I'd have to solve this for dy, then replace that, then solve it for dx, replace that. Solve this for v, replace that. So, well, actually, I would want to leave v alone. But it would be a mess. That's the long and short of it. Right? If I clean up my differential equation, the original one, to begin with, it's going to make life a lot easier. So if I do that, I'm looking at 3xy dy equals negative x squared minus y squared dx. So I'm just subtracting, and then I'm going to divide. So I'm dividing both sides by 3xy. And then I'm also dividing by dx. So I'm looking at dy dx is equal to, well, I'm going to clean it up a little bit. Instead of negative parentheses x squared minus y squared, let's make it y squared minus x squared over 3xy. All right. So again, still not proportional, but I'm going to make this substitution now. This is going to replace my dy dx. All right. So this guy's going and getting replaced with this. So we're looking at v plus x times dv dx is equal to all this stuff. I keep doing it. I don't know why. I mean, I do know why. But I don't know why I can't stop myself from doing it. All right, so seems like we made the situation much worse. It's like, oh, how is this even remotely helpful? It will be. We just have to clean it up. All right. So y equals vx. All right. That's where all this started. All right. That allows me to replace every y with a vx. So that instead of having an equation in terms of v, x, and y, it'll just be in terms of v and x. All right. So left-hand side is fine. The right-hand side, I'm going to make a couple of substitutions. So we're looking at v squared x squared minus x squared over 3vx squared. What does that simplify down to? V. No, there was definitely a minus 1 over 3v, but it was v squared, yeah. All right, every term is divisible by x squared, so we'll divide it all out. All right, so that's much nicer than what we started with, but not nice enough. All right, we want to make it really nice. All right, so let's continue. All right, so I'm going to subtract off the v from both sides. But I need a common denominator. All right, so I need to multiply top and bottom. So I'll write it as v over 1. I'm going to multiply top and bottom by a 3v. So we're looking at x dv dx so we have, this is going to be, it's not very pretty, but this is 3v squared, so v squared minus 3v squared, so negative 2v squared minus 1 over 3v. Which is proportional. Again, not pretty, but proportional. All right, x's and y, x's and v's now could be separated. So we're looking at 3v over negative 2v squared minus 1 dv is equal to 1 over x dx. So I need that, this had to go the other way, so I divided, so multiplied by the reciprocal, brought this over here. This had to go over there, so I multiplied by the reciprocal also. The x is shot over. All right. It looks really nasty, but it's actually very easy to integrate. Right-hand side, anyway, I mean, ln x plus c. So, looking at the power relationships between the bottom and the top, you can see that it's only a difference of 1, right? If I took the derivative of this, what would I get? Just the bottom. Negative 4v, right? All right, well, I want a 3v. So this is a natural log situation. So natural log of the bottom. You could even pull out the values, the negative sign and the 3 if you want, but it's not really necessary because it all comes out in the wash anyway. So I could say the natural log of negative 2v squared minus 1, that would have a derivative of negative 4v. I don't want that. I want the 3 instead. All right, so that's in lieu of performing u substitution. All right, because I think we've done enough substitutions for a question like this already. All right. Can get a little nasty, right? But and that's also why we learn about techniques of integration before we get too crazy with this stuff. All right. I can multiply both sides because if my goal here is to solve for v in terms of x, I can multiply both sides by negative 4/3. In which case I'd get the natural log of negative 2v squared minus 1 is equal to negative 4/3 ln x plus c. Convert, because remember there's an assumed e here. Log base e. So it would be e to all that equals this. So it's going to be e to the negative 4/3 ln x plus c would be equal to the negative 2v squared minus 1, which in turn would become c e to the negative 4/3 ln of x. Because that c became the coefficient, it would absorb any plus or minuses. So that would make it negative 2v squared minus 1. It could also absorb the negatives there if you wanted to. And we could do that. We could divide everything by negative 1, or we could just sit tight on that. It doesn't really make a difference at this point, because we still need to get rid of v. All right. CE, how else could I write this? The negative 4 ln root absolute x. How else can you represent a coefficient of a log? Exponent. So natural log of x to the negative 4/3. And e to the ln of x to the negative 4/3 becomes what? What happens between an e and an ln? What's the relationship? They're inverses of one another, so they cancel. So you're just going to be left with this. Do I need the absolutes anymore? No, because I asked the question, right? But what's the real reason why? Yeah, we'll go with that. That's not the real reason, though. You're raising x to an even power. Right? You're raising something to an even power. What happens? It's going to be positive. Right? So you're guaranteed a positive value. All right. So I'm going to bring down the negative 2v squared minus 1. Now the c can gobble those bad boys up and make it c x to the negative 4/3 equals 2v squared plus 1, which is why I said earlier that it didn't matter if you left the negative sign outside of the integral, pulled the 3 out. It didn't make a difference because it's all going to come out in the wash. That c is like the great equalizer. It cures what ails you. All right. Now, we do need to get an answer in terms of x solved for y. We do know that y is equal to vx. If I want to swap out the v now, because we did the integral part, and in fact, once we found the antiderivative, because that was the hard part, everything else is algebra, although you may disagree. You may think the antiderivative was the easy part. All the algebra is what made this problem suck. But the idea is that once you've taken the antiderivative, your only goal should be to get it back in terms of x and y, and then solve for y. All right? So if I want to replace the v, what relationship should I use? I know y is equal to vx. Y over x. Yeah, v is equal to y over x. So cx to the negative 4/3 would be equal to 2 times y over x squared plus 1. Sorry?
Y plus 1.
I just carried it.
Why was it there? Didn't you add 1 to both sides?
Did I?
I don't know. Oh, you divided everything by negative 1. Okay. I think that you might have added 1 to there.
So cx to the negative 4/3 is equal to 2y squared over x squared plus 1. Now it's just algebra. I mean, it's easy for me to say, I guess, but that's all it is. I got to multiply everything, I guess, by x squared, or I could subtract the 1 first. It doesn't make a difference. I'll subtract the 1 first. So 2y squared equals cx to the negative 4/3. Oh, I said I'd subtract the 1 first. Minus 1. Multiply both sides by x squared. 2y squared equals cx to the if you multiply by x squared, you're really multiplying by x to the 6/3 power. So x to the positive 2/3 minus x squared. All right. And so divide by 2. Y equals c, y squared equals cx to the 2/3 minus 1/2 x squared. Now this one, I mean, there's really a lot of different ways you can go because you have multiple x terms that are raised to a power. It's like, what form should I have my answer? Oh, pick your poison. At least you can get a solution for y in terms of x. So might as well. But again, you never know. Multiple choice can take on any form. All right, so this one, and this is more along the lines of what you'll be given. It's already given in a convenient form, so I don't have to solve for dy dx. I could perform my substitution right off the bat. So I know y is equal to vx, and dy dx, also the same as y prime in this context, would be v plus x dv dx. All right, so I can swap out the y prime for all of this. So v plus x dv dx would be equal to, and then I could replace all my y's with vx's. All right, so we're looking at, let me do that in black. X cubed plus the equivalent of y cubed, x, the equivalent of y squared. So the equivalent of y is vx. And you'll see in a sec, this is shockingly simple by comparison. So we're looking at x cubed plus v cubed x cubed over v squared x cubed. What's happening on the right-hand side of this differential equation and what happened on the right-hand side of the last one in this step, I mean, it was like an hour ago, so you probably don't remember. But you have that common x that canceled out. If that doesn't happen, then either it's not a homogeneous differential equation, which would be a problem because I said solve the homogeneous differential equation, or you did something wrong. All right? In this case, we're looking at 1 plus v squared, v cubed over v squared. So v plus x dv dx would give us that. If I subtract off the v, I get x dv dx is equal to, I just need to get a common denominator. So multiply top and bottom by v squared. And what do I get? Cancels, yeah. So I have v squared on the bottom. I have a 1 on the top. And so my differential equation in differential form would be v squared dv equals x dx, which you could then integrate much, much